Another memory management technique that is very commonly used is called paging. Paging allows us to very easily work with a larger logical address space than the physical address space. Now, what happens is that to use pages, we take our memory address and we divide it into we divide into two parts, uh, the page number and the offset. So this is my logical address and it is going to have two parts. This is called page number and this is the offset. Okay. And what happens is that there is something called the page table. As you can see that this is the page number and this is the offset. Now the offset is copied as it is into the when we are converting a logical address into a physical address. The page number is looked up in something called a page table, and the page number, say I'm looking for page number 7, so I go 1 2 3 4 and page number 7, it gives me a particular value of frame number and I take this frame number. Okay, so what we get is a new address which has frame number and an offset. This value directly comes from here, while the frame number comes through a page table. Okay, now how does this page table help us is because we have say the physical memory and it has got say 4 pages. Okay, so we start two processes. One of them requires so each of these is say 1 MB in size, right? And what has happened is that we have started two processes, each of which take 3 MB of RAM. So we have this let me just right. uh, this is a process P1, and there is another process P2, which requires another 3 MB of storage space. Okay, um, now if I have to access a particular place in this location, say I want to access this particular line. Okay, so I say that this is page number 3 and line number 10. Maybe like this is this is line number 10 in this particular page. Okay, now what happens is when process P1 is running on my memory, it might have so happened that the operating system has loaded process P1's into the space in my memory. Okay, and when I translate this through the page table, it translates into 3 comma 10. Okay, and it accesses this location in the memory, which is correct. Now what happens is now we have to load the second process into the memory. So to do that, what we do is we free up some of the space here, and we load this process here. Okay, and now I'm trying to access this place in the memory, which is maybe say 1 and page number 12, offset 12, page number 1, offset 12. Okay, now the page number which process P2 is seeing is 1, 2, and 3, like this. But in the operating system, these blocks are loaded here in number 2, 3, and 4. So when we have to access this particular block of memory, this will go through the paging table, where the operating system will translate this into 2, 12. Okay, and it will access this location in the memory, which is the correct location. So now you can see that we are able to access locations like this. So when process P2 tries to access 1 comma 12, it's actually accessing 2 comma 12 in the physical memory location. And when P1 tries to access 310, it's actually accessing 310. It could also so happen is that there is a particular process which needs maybe 4 MB of memory. That's possible, or 5 MB of memory. Okay, so now this process is not loaded entirely into the memory at one go. It is loaded part by part. So it could happen that these blocks 1, 3, 4, and 5, these have been loaded. Okay, now if these have been loaded and I try to access some memory location here, which is say 5 and 8. Okay, now when I'm trying to access this 5,8 location in my memory, it would need to be converted to 4, 8, because this 5, 8 memory location, the data that I'm actually trying to access is available in this position, right? So that's what paging is all about. There is a page number which gets translated to a frame number via the page table. The page table, there is a page table for each process. Each process maintains a page table, and whenever swapping takes place, that is a physical frame of memory. So like I was talking about this process which has 5 MB of memory. Now 5 MB of memory cannot be on the physical memory simultaneously. So obviously 1, 3, 4, and 5 is on the main memory. Where is block 2? Where is page 2? Page 2 has been swapped out to the backing store. It's not like page 2 does not exist. It exists in the backing store. When that part of the memory is needed, it will be copied into the primary store. So paging allows us to actually make the processes believe that they have this contiguous set of 5 pages of memory, while actually we have only 4 of them loaded into the memory. One block is there in the backend store. It can be brought into the foreground when it is needed, right? And when the process is trying to access a memory, it just tells the virtual address, which is page number 5, address 8. The operating system understands that this data is actually kept in frame number 4 and address 8, so it fetches it from there, right? So this is what paging is about.